evening, all the viewers. Today, I will discuss about one of the major topic in fluid dynamics, that is flow rate measurement using Venturmeter. Myself, Anish Mangal, Assistant Professor in Department of Mechanical Engineering at ABES Engineering College. So let us see the topic in detail. First of all, I would like to discuss about Venturmeter construction. What is a Venturmeter? And basically, what is the construction part of Venturmeter? So let us see. Venturmeter is a device which is used for measuring the rate of flow of a fluid flowing through a pipe. So basically, there are several devices which are used for measuring of rate flow, uh, like Venturmeter, orifice meter, and rotameter. But here we will discuss about Venturmeter. Now see the construction of Venturmeter. It consists of a converging part, which is a small part, or you can say a small zone, which is having the decreasing area. Then in between there is a throat, which is having the constant area. And finally, it is having a diverging part or diverging cone, which is having the increasing area. So these are the three components of the Venturmeter, which are fitted in a pipeline. Okay, so these are basically fitted in a pipeline. Now, let us see. This basically a Venturmeter is also fitted with a manometer. Okay, you can see in the diagram. Here you can see a YouTube manometer, which is a differential manometer to calculate the pressure difference at point 1 and 2. Okay, so the point 1 is taken at the inlet of Venturmeter, which is fitted in the pipeline, horizontal pipeline in this case, and point 2 is basically connected with a throat. So the difference of pressure between the inlet of Venturmeter and throat is calculated by this U-tube manometer. This height, small h, you can see in the diagram, is being observed here in the laboratory. So here we are taking D1, that is the diameter of the inlet of the Venturmeter, and the flow direction from left to right. Okay. Now see, you can see here, it is the diagram, or you can say Venturmeter in real, how it looks like. So you can see easily that at the inlet side, there is a connection for connecting in the pipeline, and it is basically having three sections: converging, throat, and diverging. Okay, and there are two taps given over there. One is at the inlet tap and second at the throat. So these taps are connected with the pressure gauges in case if YouTube manometer is not connected. Okay, now basically when we talk about Venturmeter principle, what is the principle? It is based on the Bernoulli's equation, and as we know that Bernoulli's equation is basically the conservation of energy. It includes the three heads, that is the pressure head, kinetic head, and the potential head. And the sum of these heads, or you can say energy per unit weight, is remain constant. So this is the Bernoulli's principle, and according to it, the velocity head increases in an accelerated flow by reducing the cross-sectional area of the flow. Okay, so here in the converging portion, when the cross-sectional areas reduces, then the velocity head increases, but the pressure head is reduced. Okay, due to the conservation of energy. Okay, now after that, a pressure difference is created, which enables the determination of discharge through the pipe. Basically, the pipe is connected, and the pressure difference is being created at the inlet side and the throat side, because after the converging portion, the throat is having the fixed area or constant area, and you can have the pressure which is varying from the inlet side. So this pressure difference has been observed by the manometer or either the pressure gauges. So this is the basic principle of Venturmeter. Next, we can see derivation for the flow rate. Basically, Venturmeter is used for calculating the flow rate. So here you can see, consider a Venturmeter fitted in a horizontal pipe. Okay, so first of all, we are taking a horizontal pipeline and the Venturmeter is fitted in this. The fluid is flowing from left to right, as I have shown you earlier in the diagram. So here we can consider some parameters. D1, that is the diameter at the inlet. P1, pressure at section 1 or the inlet. P1, velocity at section 1. A1, area at section 1. So all these components, or you can say the parameters, are considered at section 1. And similarly, some parameters D2, P2, B2, A2 are being considered at the throat section, that is the section 2. Because I told you earlier that section 1 is the inlet of Venturmeter and section 2 will be the throat. Now, when we consider these two sections, we apply simple Bernoulli's equation, that is, you can say, having the assumptions for the ideal fluid flow and steady state equation. So here we can have some simple Bernoulli equation between section 1 and 2, which is in this form: P1 upon rho g plus V1 square upon 2g plus Z1. That is the sum of three heads, or you can say the sum of the three energies per unit weight at the section 1, and this will be equal to the energies per unit weight at the section 2, that is P2 upon rho g plus V2 square upon 2g plus Z2. So basically this resembles, or you can say this shows a particular conservation of energy. Now we have taken the horizontal pipelines, so that's why Z1 is equal to Z2. It means the datum head or potential head from the ground level of the section 1 and 2 is same. So that's why Z1 is equal to Z2, and this will be cancelled out from both sides. Now we can see the equation reduces to P1 minus P2 upon rho g is equal to V2 square minus V1 square upon 2g. Here we are considering P1 minus P2 upon rho g as a small h. Now what is this small h? That is basically the difference of pressure head at section 1 and 2 obtained by observing the difference of water column in the two sides of U-tube manometer. So if we are having the manometer connected with the Venturmeter, then when we observe the difference of water column at section 1 and 2, then this difference of pressure head is denoted by small h. So here we can easily write P1 minus P2 upon rho g as a small h, and it is equal to V2 square minus V1 square upon 2g. So this is, you can say, the first step of the derivation for the flow rate to obtain the value of small h. Now, moving further, we can apply here continuity equation between sections 1 and 2. So when we apply continuity equation, we have to see that it is for compressible or incompressible flow. Now, in this case, as we are applying the Bernoulli's equation with some assumptions, we are taking the assumption of incompressible flow. That is, the density of the fluid at section 1 and 2 remain constant. So in that case, the continuity equation will become A1 V1 is equal to A2 V2. And from this equation, we can obtain the value of V1 is equal to A2 V2 upon A1. So by obtaining this value of V1, we can put it back in the equation of small h. In small h, we will get here V2 square minus V1 square upon 2g. So we can put here V1 value that is been obtained from the continuity equation. So by solving the value of V2 from the above equation, we have the value of V2 as A1 divided by square root A1 square minus A2 square and multiply by root 2gh. This is the value of V2. Now, as we obtained the velocity at section 2, we can multiply by the area at section 2. And A2 V2 will be the discharge or flow rate capital Q. So in this way, we can obtain the value of Q, capital Q, that is the flow rate at any of the point. So A1 V1 should be equal to A2 V2 as per the continuity equation. So we can put here the value of V2 and multiply by A2. So the formula for the discharge or flow rate will be A1 A2 divided by square root A1 square minus A2 square into root 2gh. But as you know, we have derived this formula by the theoretical laws. Then this is called the theoretical discharge, which is being obtained under the ideal conditions. So this is basically called a theoretical discharge. But when we perform experiment in the laboratory on Venturmeter, the actual discharge, which is being observed by the collecting tank, we can have a collecting tank there, and the flow rate can be observed by the filling of the tank, and we can observe the reading in the piezometer, and the initial and final readings will be taken off in a particular time interval. So this will provide the discharge in actual condition, and that will be the volume upon time. So basically, volume will be the area of the tank multiplied by the delta H, that is the height which has been raised during a certain interval of time. And this volume divided by time interval will be the actual discharge. So this ratio of actual discharge and theoretical discharge will be called as a coefficient, which is called the coefficient of discharge, CD. So here we can write actual discharge Q actual will be equal to CD multiplied by Q theoretical. So in this way, Q actual is equal to CD times A1 A2 divided by square root A1 square minus A2 square into root 2GH. So this will be the equation for actual discharge from, you can calculate from a particular Bernoulli's equation and the continuity equation for a Venturmeter. Okay. So in this way, we can use this equation to calculate the flow rate or discharge flowing through a pipeline. After that, applications of Venturmeter. Now we can see Venturmeter is a very useful device to calculate the flow rate. So it is being widely used in many of the industries, which includes gases, liquids, slurries, suspended oils, other processes where permanent pressure loss is not tolerable. So in this way, Venturmeter can be used widely. Second point, it is widely used in large diameter pipes such as found in the waste treatment process. So wherever the waste treatment process has been going on, we can apply the Venturmeter at the large diameter pipes. It will be helpful to calculate the flow rate in that case. It allows the solid particle flow through it because of its gradually sloping, smooth design. So basically, due to the sloping design, gradually sloping, it can be used to allow the flow of solid particles. So they are suitable for measurement of dirty fluids. So basically, whenever there is a slurry or you can say dirt in the fluid, it can be used easily to calculate the flow rate. Next will be it is also used in the medical sector for the measurement of flow rate of bloods in arteries. So basically nowadays, it is also useful in the medical applications such as the measurement of blood flow rate in the arteries. So these are some of the applications of Venturmeter, how it can be used in different industries that I told. Now see one numerical on the Venturmeter. This is a question given in a 100 mm diameter horizontal pipe. A Venturmeter of 0.5 contraction ratio has been fixed. Okay, so here it is given 100 mm diameter horizontal pipe. So the inlet diameter will be the 100 mm D1. Venturmeter of contraction ratio. So basically 0.5 contraction ratio. It means we can calculate D2 is equal to 0.5 times of D1. That means the contraction ratio is 0.5. So after that, the head of water on the meter when there is no flow is 3 meter gauge. So here it is given the value of head of the water, and I told you that head will be pressure divided by rho times G. So this value, when there is no flow, it means the inlet condition will be 3 meter gauge. But if we find it in the absolute terms, so the absolute pressure at any point will be the gauge pressure plus the atmospheric pressure. So in the question, it is given also that atmospheric pressure head in terms of water column will be 10.3 meter of water. So this value we can add in the 3-meter gauge. So it will be the absolute pressure head at the inlet. Now, what is the question? That find the rate of flow for which the throat pressure will be 2 meter of water absolute. So the throat pressure is also given, that is 2 meter of water absolute. So it is given in the absolute terms. So we don't need to add up the atmospheric pressure head. So that's why total pressure at the throat as well as at the inlet side will be given. Now we have to calculate the flow rate, that is capital Q, and CD is given 0.97. So simple, we have to apply the formula for Venturmeter flow rate. You can see these are some of the you can say solution part, and in this first of all write the given parameters. Always solve a numerical by putting all the data given and then starting solving the numerical. So D1 it is given. A1 we can calculate, it is a circular pipeline, so the area will be pi by 4 D1 square. Similarly D2 is 0.5 D1s because the contraction ratio is 0.5. So we can calculate D2, and A2 similarly can be pi by 4 D2 square. Now, after that, I told you that P1 upon rho g is given 3-meter gauge. We can add 10.3 atmospheric pressure head. So it will be 13.3 meter absolute pressure at the inlet. Now, similarly, throat pressure head P2 upon rho g, because the second section will be at throat. So it is equal to P2 upon rho g, and it will be 2 meter absolute in absolute terms, 2 meter of water volume. So P1 upon rho g minus P2 upon rho g will be small h, as in the derivation I shown you earlier. So small h will be 11.3 meter. After that, the formula for Q, that is the Venturmeter flow rate, it is CD if we are calculating the actual discharge. Then CD into A1, A2 divided by square root A1 square minus A2 square multiplied by root 2GH. So CD is given in the question 0.97, A1, A2 that we have calculated earlier, and multiply by root 2GH. H is also been calculated in the previous step. So we can put all the values here and solve for the value of Q. So in this way, in this question, the Q is coming out to be 29.306 liter per second. We have converted centimeter cube per second into liter per second. And what is the conversion? You can say 1 liter will be equal to 10 raised to a minus 3 meter cube. So by using this conversion, we can easily convert centimeter cube to liter, and the final answer will be 29.306 liter per second. Because many times the answer is to be asked or you have to solve it in the liter per second. So in this way, some numericals can be done on this topic, because it is having very much application in the industries as well as medical field. So the formula for Q is very useful. References: a textbook of fluid mechanics and hydraulic machines by Dr. R.K. Bansal. So thank you.